Okay, so the plan for today is just to continue on with chapter 5, systems of linear equations. Um, it's not technically part of the course, somewhat ironically for an algebra course. Sections 5.2 and 5.3. At CCAC, the way that we've structured our curriculum, we choose to leave that until Math 108. But I would like to go through just a brief discussion, just show one example of some of each of two algebraic solution methods. So we talked about solving systems graphically, but I would like to take a little diversion, talk really quickly about some algebraic solution methods, just so you have a little bit of a heads up of what you'll see in Math 108. And if you want to solve the systems this way, you're certainly more than welcome to. And probably throughout one or two of the other problems, I also throw in maybe along with the graphical solution method and algebraic example. And then 5.4 and 5.5 are on solving applications, either general applications or mixtures. So that's the plan for today. Super important note. I checked WebAssign this morning right before class, and only about a third of folks registered for the class have completed the exam or the examinee practice exam. The examinee practice exam has been up for a few weeks now and was supposed to be completed more than a week ago. That's the one where you go into Examity, log into the exam, make sure all the technology is working properly and all of that. And then my advice for the exam was not to wait until the last day. If something, there are no due date extensions. So if something goes wrong, waiting until the last day leaves you with very little margin on an assessment that's worth 15% of your grade. So, so that Unit 1 exam is due today. At this point, it's already last minute. So I would recommend not waiting much longer. So, as soon as you're able to get it, and I know some folks have emailed me, last week or over the weekend or something, and are kind of working on it. So if you're in that situation, like, keep working on it. But if you're, especially for Unit 2 exam, I would strongly recommend not waiting until the last day.
Excuse me. I have a question.
Sure.
It's asking for a password, and I'm trying to take the picture. I'm trying to log in.
Mm-hmm.
I just couldn't get it.
Yeah. So on one hand, that's the purpose of the examinee practice exam, is to go through all of that before the exam is due. But yeah, so just kind of a short rundown. And the previous Blackboard announcements also kind of address this a bit. The exams on WebAssign are password protected, and that's so that you don't accidentally open the exam outside of the Examity system. So that's the point of the password protection, because they have to be taken while they're proctored. So just so that there are no mistakes where somebody, accidentally opens the Unit 1 exam when they meant to open the sample exam, both the Examity practice exam and the actual Unit 1 exam are password protected. So you go to Examity, open up your Examity session, and then the Examity browser extension will enter the password for you. You click a button on the browser extension, it enters the password for you, and then you can get into the exam. So if you go through the Examity practice exam and read through all the documentation that I send out, the Examity user guide, or the video that from, I think it's maybe Harrisburg Area Community College, something like that walks you through some of those details. I can send out, I think I have a couple other videos that I sent out to a couple of students in my other class who had some questions, so I can post those as well. But yeah, there's also on the Examity website, there's a little link at the top that's something like watch a 5-minute tutorial or something like that. You can watch that, so that those all walk you through how to do it. But that's why it's so crucial to do the Examity practice exam weeks in advance, just in case any of that tech doesn't work. But at this point, we're kind of, at the 11th hour. So Yeah, so use all of those resources. That's how the password and all of that works to get into the exam.
Well, it would not open up for me. I tried to do everything that it was telling me to do.
Okay. Yeah, I mean, if you wanna stick around during office hours, I can help you out individually.
Okay.
Yeah. Yeah, I have office hours right after class today. So if anybody wants to hang out during office hours, we can take a look at what's going on.
Okay.
Okay, so the quote of the day today is by Charlie Munger. So if any of you know like Berkshire Hathaway, Warren Buffett and Charlie Munger have run a big company called Berkshire Hathaway for a very long time. Charlie just died in the fall. He was almost 100 years old, still at the helm of Berkshire Hathaway, as is currently Warren Buffett, who is also in his 90s. And in their shareholder meetings, people will ask them questions, and Warren will always give a careful, measured response, and Charlie will come back with some kind of snarky point. So it's always fun to watch him. But he has a lecture called Psychology of Human Misjudgment, and this is from roughly 24, 25 minutes into the lecture. It's a great lecture you can find it on YouTube. Just look up Psychology of Human Misjudgment. It's about an hour long. And basically it talks about how people misjudge things related to economics and finance. But I think the general concepts apply much more broadly to life in general. But one of his funny quotes from that lecture is, "Better to add a sigma than change a theory." And this is a stats idea, so it requires a little bit of background. I kind of use this quote of the day for my stats class, but so a little bit of the background is he's talking about the efficient market hypothesis, which Berkshire Hathaway kind of stood in the face of. So the efficient market hypothesis is this statement that you can't beat the market on average over a long period of time. And Berkshire Hathaway beat the market on average over a long period of time. So when this Nobel laureate economist, who won his Nobel Prize for the efficient market hypothesis, when people would ask him, well, what about Berkshire Hathaway? You have this model, you claim that your model holds in the real world, but Berkshire Hathaway, they beat the market on average over a long period of time. And he'd say, oh, well, that's just kind of a rare event. Basically, they just got lucky. And he would say, oh, well, that's just a 2 sigma event. In other words, it's something that happens, it's a 2 standard deviation event. It's something that happens maybe 5% of the time. These things happen sometimes just by chance, right? If you flip a coin a bunch of times, just by chance, if you flip long enough, you'll get, say, 10 heads in a row. And then a couple of years later, they're still doing well. And somebody asks them, wait, they're still doing well. They're still beating the market on average. It's a 3 sigma event. And Charlie says he got all the way up to 6 sigmas because it's better to add a sigma than change a theory. So instead of saying maybe my life's work, maybe my model doesn't apply 100% to all situations universally, maybe I need to adapt my theory and be a little more careful with what assumptions I'm making and adjust my theory to the real world data. He'd rather just say, oh, well, that real world data that you're positing that's against my theory, it's just very unlikely. It's just very unlikely to happen. It's a fluke event. And then he doesn't have to change his theory. So I think this is particularly valid when we're talking about either statistics or what we're talking about today, mathematical models.
They own so many companies. I looked it up just now because I was like, I have no idea what Berkshire Hathaway even is.
Yeah. It's more or less it's an investment company. They have a real estate division. Sometimes you'll see their little like archway shaped real estate signs, for sale signs in front of people's houses. But yeah, I mean, their most famous holding is probably Coca-Cola. They own Geico.
They own
Some other
Dairy
things,
Queen,
Bank of
apparently.
America. So a lot of things that you've heard about. So as an aside, Warren and Charlie's investment philosophy is they want to look for companies that have good leadership, so good CEOs and executive leadership and so on. That's good for the stability of the company. And where the American mind has a positive view of that company's name. So like everybody likes Coca-Cola, right? Even if you like Pepsi better than Coke, it's like you're not like, oh, Coke, that's like horrible or something. So it's very entrenched in Americans' minds that Coca-Cola is like a positive in some sense. Maybe not so much Bank of America these days, but at least everybody knows what Bank of America is, and they're probably not, you know, any more annoyed with Bank of America than they are with Chase or BNY Mellon or any of these other ones. Yeah, but I think this is particularly applicable to what we're discussing today. We're coming up with mathematical models. We have the real world. We're trying to model it mathematically. And it's important to understand that our models, that the real world doesn't follow our models, but our models approximate the real world. If I develop a model, and if it's a beautiful model with all kinds of great theoretical support, and I can have a really clear argument as to why that model is correct, and I go into the real world and this model simply doesn't work, if it just doesn't mesh with real world data, then my model's wrong. It's not that the real world is wrong. It's that my model needs to be adjusted, or at the very least, I need to accept the shortcoming of my model and say that that's, that my model doesn't apply 100% in all cases. So that's, Charlie Munger's kind of snarky way of saying that. But if you're interested in finance, you can look up on YouTube their shareholder meetings, the Berkshire Hathaway shareholder meetings. People have posted it everywhere from just little 1-minute clips of Charlie's little snarky answers, or Warren's, more in-depth economics and finance answers, all the way up to, I think, probably not the whole meeting. I think the whole meeting is like many, many hours long, but there's bigger chunks of the meeting available too. So that's the quote of the day for today. And the idea is just remember that all of our models, whether it's a mathematical model or a model in biology or a model in economics or whatever, these are approximations to the real world. The real world is the arbiter of truth, not our models. The world doesn't follow our models. Our models approximate the real world. Okay, so let's jump into solving systems. We're going to start with a fairly simple system. We're going to solve it graphically. And then
hey, Professor, I guess I could talk to you about the examining thing during office hours.
Yeah, if anybody has,
I don't mean to interrupt you or anything.
If anybody has questions about the exam or examity, like I mentioned before, just stick around to office hours. Yep.
Okay.
Yep.
Never mind.
Yeah, if you just want to pop into office hours, we can chat whatever you want to talk about the exam or examity. But let's move on to the material for today. So let me get my screen share switched over here so that we can get the calculator on the screen as well. All right, so let's start with this example. We want to first set up a system of equations. So we've seen actually problems similar to this one back in chapter 3 when we talked about applications of linear equations. And back then we kind of, just muscled our way through it. Here we're going to try to be a little bit more algorithmic. We're going to try to follow more of a set process. So we're going to look through the problem. We're going to set up a system of equations. We're going to be looking for 2 equations and 2 unknowns. And then we're going to try to solve those equations graphically. And then as kind of a side note, we'll do a couple of them algebraically, just to show that example, even though, as I said, solving algebraically sections 5.2 and 5.3 isn't technically part of the course. just because of the way we've structured our curriculum, but just to give you a little bit of insight into how that works. Okay, so I see I have the wording, the sum of two numbers is 12. So again, I pick out my is, that probably means equals. The sum of two numbers, let's call them X and Y, and that sum is 12. So I think one of my equations I get right away is just X plus Y equals 12. And then I have that one number is 7 less than the other. Now, which one do I pick to be X and which one Y? It actually doesn't matter. The sum of two numbers, this is commutative, right? So whether I picked the first number that I'm adding together is X and the second Y or vice versa, it doesn't matter. I get the same answer. So since X plus Y equals 12 or Y plus X equals 12, it doesn't matter which order I pick my variables in here. So I'll just say that one number is 7 less than the other. So what's the other one? Y. But 7 less than Y is Y minus 7. A little confusing there when we have something like the word less than. We might get tripped up. We might think, oh, does that mean like a less than symbol? In this case, no. We might think, does this mean like 7 less than Y or something like that? But if we think about that, it's no, if X is 7 less than Y, then X is Y minus 7. We have the amount that we have for Y, take away 7. So it's not this either. So we just have to be a little bit careful with this wording. Sometimes in this case, it's, written a little bit backwards maybe of the way that we end up writing it in the equation. So this is my two equations and two variables. Now let's try to solve this graphically. So if I want to solve graphically, I would like to, we could, if we wanted to solve for X in terms of Y. We could solve for Y in terms of X. It doesn't much matter. In this case, I have X equals Y minus 7. So I'll come up here and I'll solve for this as X in terms of Y. So X equals minus Y plus 12, and X equals Y minus 7. There's nothing wrong with solving for X in terms of Y. These are just two variables. And again, I can graph X versus Y, or I can graph Y as the independent variable, Y on the horizontal axis, X on the vertical axis. It doesn't much matter. When we're thinking of something like a function, a functional relationship between X and Y, it's maybe a little bit more important to keep our X's and Y's sorted. But here we just gave the names X and Y to these two variables, so it doesn't matter a whole lot how we graph them. But I'm going to graph with Y on the horizontal axis and X on the vertical. Just to really make the point that we just named two variables arbitrarily. It doesn't much matter how we solve for them or how we graph them. It doesn't much matter what order we do any of this in. And if you had chosen to solve for everything in terms of Y equals stuff, and then graph with the horizontal axis being X and the vertical being Y, that's fine too. So I have X equals Y minus 7. I'm going to pick some values of Y, find the corresponding values of X. So for instance, when Y is 8, 8 minus 7 is 1, or 9, 2, or maybe 7, 0. And similarly for the first equation, x equals negative y plus 12 or 12 minus y. So when y is 12, x is 0. When y is what, 0 maybe, x is 12. And when y is maybe something like 6, x is 12 minus 6, or also 6. So I could use kind of intercepts and then a third point, or I could use just convenient values of one variable and then solve for the other one. So let me try to be somewhat careful drawing my axes, my grid lines and all of that. I see that my y's go from 0 to 12. I have a 0, 6, 7, 8, 9, and 12. So maybe I'll go like, I'll use tick marks of say size 3. I'm trying to make them pretty equally spaced. Again, I'm solving this graphically, so I need my picture to be pretty reasonably accurate in order to generate a pretty good guess. And then my x values also go from 0 to 12. So I'll do kind of the same thing. Okay, so equation 2, maybe I'll draw this one in blue, goes through 9, 2. So that's maybe about here. Goes through 7, 0. So that's maybe about here, a third of the way between 6 and 9. And 8, 1. That does seem like it's on that same line. And then equation 1, maybe I'll draw it in green. We go through 12, 0, 0, 12. And I'm going to draw this line before I draw the point. I'm going to cheat a little bit. I'm going to draw the line and then see if I think that the 0.66 does fall on that line. And that does look pretty good. And remember, what I'm looking for is I'm looking for an ordered pair, in this case, y, x, where that choice of y and x simultaneously solve both equations. Or another way of saying that, I'm looking for an ordered pair that's simultaneously on both the green line and the blue line. I'm looking for an intersection between those two lines. And it kind of, just eyeballing it, looks like it might be maybe y equals 9, x equals 3. Something like that. So yeah, y equals 9, x equals 3. It looks like that might be about right. If I plug in here though, 9 minus 7 is 2 though. Yeah. 9 minus 7 is 2, and negative 9 plus 12 is 3. So I think I'm off a little bit. I'm pretty close, but I'm off a little bit. Let me go over to my calculator to help me out just a little. If I come over to my calculator, I can get a more accurate picture, and I can search for the intersection. So here, I'm going to just I have one variable equals negative the other variable plus 12. In my calculator always calls the variable by itself y, and it always calls the variable on the other side x. If I have different names for my variables, I just adjust when I go over to my calculator. So my first equation is negative variable plus 12. My second equation is variable minus 7. And looking at my picture over here, I think a window of something like 0 to 12 on both axes should look pretty good. So let's graph and let's see if we get a pretty good picture. And then if I do, remember, second trace brings up my calculate menu, go down to 5 for the intersection. I see that it's selected one curve as my first curve. That looks good. The other one is my second curve. And then I just hit enter again for the guess. And I see that my guess of 9, y equals 9, x equals 3 was pretty good, but not quite right. The calculator helps me get a little more accurate and find 9.5 and 2.5. And let me verify these. Is it true that 2.5 equals negative 9.5 plus 12? And that is true. Is it true that 2.5 equals 9.5 minus 7? And that is also true. So this is indeed a solution. And we can see that it's the only solution. It's the unique solution to this problem. So we can go through algebraically, right? We tried to solve it by hand. We got an answer that was close, but sometimes, you know, for things like this, where the answer is fractional, it can be really hard to tease out on a drawing by hand exactly where that intersection is. You know, it looked like it was more or less y equals 9, x equals 3, and that got us pretty close, but not right on. The calculator helped get us the exact answer. So that's one of the shortcomings of the graphical approach, is we're either reliant on the calculator to get good accuracy, or we're our drawings by hand are really only going to be accurate enough when we're looking for, say, something like integer solutions or solutions that fall on a pretty clear grid point. So let's take a look at a couple algebraic methods. So I'm just going to kind of come off to the side here. I'm going to rewrite our system. And here, instead of solving both equations for one variable, I'm going to put all of the variables on the left side. So x equals y minus 7, I'm going to write as x minus y equals negative 7. And again, this isn't technically material for this course. This is technically material that in our curriculum we cover in 108. But as you can see, the textbook includes it in this chapter. This is, I think, that it's material that's accessible to in MAT090, certainly. And you might want to go this route when solving equations. If you do, perfectly fine. If you don't, if you want to stick with the graphical method, that's fine as well. It's just a curriculum choice that we made based on where the different material seemed to fit the best for both time and complexity. So for algebraic solution methods, we basically have, there are many algebraic solution methods, but for our purposes, we basically have two methods. One is called the addition or the elimination method, and the other is called the substitution method. And we actually used this method in section 3 or chapter 3, and just didn't really call it this. So when we see the substitution method, we might realize that we had even used that before and just didn't really formally call it that. So the idea of the addition method, let's do that first. And again, this is just kind of side material. If you like this method better and you want to solve the equations this way, go for it. If you don't like this method, then just use the graphing. The idea of the addition method is, let's just take, for instance, our first equation. I can manipulate this equation in various ways. I could say, for instance, I could choose to add 5 to both sides. Right? I could do that if I wanted to. Maybe I want to, maybe I don't. It doesn't seem like it helps all that much in this case, but I could do it. It's not invalid. I could, subtract x from both sides. My x's go away on the left. Again, something I could do if I wanted to. Maybe I want to do it in this case, maybe I don't, but I could do it and it doesn't make an invalid statement. It's a valid, something like equation solving step, even though we're not really solving an equation at this point. Right? We're not going through that same equation solving process, but it's a valid manipulation of the equation. I could even, add something like x plus 5 to both sides. What would I end up with here? I would end up with x plus x, or 2x plus y plus 5 equals 12 plus x plus 5. I could do that. That's not a problem. So I could add algebraic structures to both sides if I wanted to, I suppose. I could even do something like, I could add 1 to this side, and I could add 3 minus 2 to that side. I mean, it's kind of a funny thing to do, but I suppose I could do it, right? I've just added 1 to both sides. It just looks a little different on both sides. Or if I wanted to, I could add -7 to both sides. Now, maybe I'll keep the -7 on the right just as a -7. But I also know something that -7 is equivalent to. It could be something like -10 plus 3 or something like that. That could be another way to say -7. But another way to say -7 could be, in this case, x minus y. So maybe on one side, I choose to add -7. And on the other side, I choose to add something that is equivalent to -7. X minus y. Through equation 2, these are equal. These are just a restatement of the same thing. I've added the same thing to both sides. I just happen to make it look different on one side than the other. Now, why would I want to do this? On the right side, what do I get? Well, 12 plus -7 is 5. On the left side, what do I get? I get x plus x is 2x. But y plus a negative y minus y, the y's actually go away. I've eliminated one of my variables using addition of the two equations. I just added the two equations together, is in short what I did. And I can see x equals 5/2 or 2.5. So one of the valid system solving steps is to add one equation to the other. And that's the idea behind the addition elimination method, is if my equations are set up like this one, we're adding one to the other. If I think of adding down these columns, I see I get a plus y minus y. Those are going to go away. My y's disappear. I'm left with just one equation in one variable, and then I can solve that. That's just the linear equation in one variable. So I can add one equation to the other, in addition to all the other things I can do to manipulate equations. I can, like I did to get it into this form, I can say solve one equation. I can solve one equation for one or the other of the variables. I can move a variable to one side or the other. I can multiply both sides by the same number or add the same number to both sides. So that's the idea of the addition or elimination method. I'm looking to come up with a structure where I can add my two equations together and eliminate, as a process of that addition, eliminate one of the variables, leaving me with just one equation and one variable that I can then solve. And then if I know that x is 2.5, how do I find y? Well, I plug back into either equation. So maybe x plus y equals 12, along with x equals 2.5. So I'm just plugging 2.5 back in here for x, and this tells me that y has to be 9.5. Once you get used to this, this can be more efficient than the graphing method. Sometimes the graphing method gets us the right answer pretty quickly, but these algebraic methods always get us an accurate answer reasonably quickly. So a second algebraic solution method, let's just copy this over here. In this case, I'm going to leave my second equation in this original form, x equals y minus 7. So my second algebraic solution method, the substitution method, is going to look kind of familiar. What's the idea here? Well, I have an equation, x plus y equals 12. But I also have another relationship between x and y, that x is just y minus 7. So everywhere that I see an x, I can just swap it out for y minus 7, which is the same thing as x. So by solving one equation for one of the variables, this one was already set up as being solved for one of the variables, and then substituting in the other equation everywhere I see that variable, this again leaves me with one equation in one variable. I should be able to solve this. I get 2y minus 7 equals 12. 2y equals 19, or y equals 19 halves. Well, that's 19 is 18 plus 1. So 19 halves is 18 halves plus 1 half, or 9.5. So I see that y equals 9.5, and then I can plug back in. Typically, I'll plug into the equation that I solved for one of the variables. The variable I solved for was the one that I solved for originally, was the one that I did not get the solution for. So now x equals 9.5 minus 7, or 2.5. Now, just to be clear, I would not typically, if you were on an exam or doing homework or something, typically you would not solve one problem 3 different ways. You would either do the graphical method, or you would do the addition elimination method, or you would do the substitution method, depending on what seemed to fit better for that problem, maybe what the instructions of the problem were, or how the problem was set up. This problem is kind of naturally set up for the substitution method because one of our equations is already solved naturally for one of the variables, makes it very easy to substitute. To do the addition method, I had to actually manipulate things to get my x's and y's all on the left side and be able to kind of add them up more easily. So maybe substitution method would be the better of the algebraic methods here. So I just wanted to show those to you as an aside, both as kind of a little bit of a taste of what you'll see more in depth in Math 108, but also just as an alternative couple of methods if you prefer these methods to the graphing method. But again, just the way that we've structured our curriculum, our focus is technically going to be on the graphing method, even though as we go through our examples today, I might solve 1 or 2 in addition to the graphing method. I might show you, maybe one more example of the addition method and one more example of the substitution method, just to get a little practice. Okay, so let's look at the next example. So the Jones family took a 24-mile canoe ride down the Indian River in 3 hours. After lunch, the return trip back up the river took 6 hours. Find the rate in miles per hour of the canoe in still water and the rate of the current. So let's draw a picture. Sometimes it can be useful to kind of draw a picture. So we have a river with a current. So unfortunately, current and canoe both start with C, but maybe I'll call the current speed W for water, the speed of the water. And then I have a canoe, which I'll just draw like this because I'm not an artist. And the canoe has its own speed independent of the water speed. So if it was in still water and the person's paddling along, how fast can they go? Maybe I'll call the canoe speed B for boat. So we have the speed of the boat B and the speed of the water W. Okay, so they traveled down the river in 3 hours and then back up the river in 6 hours. Now, an implicit assumption we're making here is that the current speed stays the same, that the speed of the water doesn't change, and also that the speed of the canoe doesn't change. I mean, after 9 hours of paddling, that might not be super true, right? But we're coming up with a model here. When we develop a model, we want to make enough simplifying assumptions that we actually come up with something that we can actually use and solve. It's not such a complicated model, we can't get a solution from it. But we don't want to make so many crazy assumptions that it's just completely disjoint from reality. So there's a balance there. Again, going back to Charlie's, statement, like there's a balance to be had anytime we're applying a model to reality. So we're assuming a constant canoe speed and a constant speed of the water. So the distance traveled is 24 miles in each direction. So they travel 24 miles one direction, then 24 miles the other direction. The time is 3 hours or 6 hours, depending on which direction they're going. When they're going in the direction of the current, their speed is being added to the speed of the current. So when their speed gets added to the speed of the current, they're going faster. They're going to cover the 24 miles in less time. So the rate is going to be B plus W associated with the 3-hour time period to cover the 24 miles. That's when they're going with the current. When they're going against the current, they're fighting against the current. That's when it's going to take them longer to cover the same distance. And when they're fighting against the current, they're going with their speed. Let me take a smaller eraser here. When they're going against the current, when they're going this way, their speed B is going in one direction, but the water is trying to push them in the other direction. Their effective speed is B minus W. So if they're paddling at 5 miles per hour, but the water current is 2 miles per hour, they're going effectively like 3 miles per hour. Not the answer here, but just to give an example of what it might look like. And again, I know that B plus W has to go with 3 hours because that's the faster speed covering the same distance in shorter time. And B minus W is the slower speed covering the same distance in more time. And I know that distance equals rate times time. So on one hand, I have that rate times time, or 3 times B plus W equals 24. And on the other hand, I have that 6 times B minus W equals 24. And maybe to make these a little easier to graph, I'll divide both sides by 3 for the first equation and by 6 for the second equation. So 24 over 3 is 8. And then 24 over 6 is 4. And maybe here I'll solve everything for B. Subtracting W off of both sides in the first equation gives me that B equals negative W plus 8. Adding W to both sides in the second equation gives me B equals W plus 4. So I'll treat W as my kind of X variable, and B is my kind of Y variable. So from equation 1, which I'll do in blue, I know that when W is 8, B is 0. And when W is 0, B is 8. From equation 2, I know that when W is 0, B is 4. I know I'm going to be looking for a first quadrant solution here where B is positive and W is positive. So maybe instead of doing something like W is negative 4, B is 0, maybe I'll try to find another first quadrant number, maybe like 2, 6. So I see W goes from 0 to 8. B also goes from 0 to 8. For my first equation, which I'll do in blue, I have a point 8, 0 and 0, 8. And then maybe I can add a third point in to check. Maybe when W is 2, B should be 6. Does this look like it goes through 2, 6? Yeah, I think that's plausible. So it seems pretty reasonable. For my second equation, I'll plot in green. I have 0, 4. and 2,6. I actually accidentally found the solution, but and let's draw the line and just check for formality's sake, I suppose. If we were to do something like W equals 4, B would be 8. Is it plausible that this goes through 4, 8? Yeah, I think so. And again, we just happen to find our solution 2, 6, which we happened on just as a part of finding the graph, or which we would have been able to search for an intersection and maybe estimate that it's at W equals 2, B equals 6. We would plug back in, is 6 plus 2 equal 8. That's correct. Satisfies the first equation. Is it true that 6 minus 2 equals 4? That's also correct. So I'm happy with this solution. If I wanted to use the calculator, once I got things into, in a sense, y equals some stuff with x, my first equation is negative x plus 8. My second equation is x plus 4. The window that I'll use, 0 to 12 on both should work again. That's good enough. And I see my intersection. I might guess that it's at 2 on the horizontal axis, or x equals 2, or in other words, w equals 2, and b equals 6. I might guess that, or I could do second trace in my calculate menu, option 5 to find the intersection, enter for the first curve, enter for the second curve, and just hit enter again for the guess wherever it is. And I do find my intersection at 2, 6. So I get my solution here. I get that the speed of the boat is 6 miles per hour. The speed of the current is 2 miles per hour. Any questions on this one? Okay, so let's work through a similar one. Oh, I'll leave this one on here. Let's work through a similar one here. We'll take about, let's say about 4 minutes. Actually, maybe about 5 minutes, because we need to set up the system and all that. So we'll take about 5 minutes for this one. So work through this one. We'll come back in about 5 minutes, talk through the answer. And as usual, I'll kind of, jot down a few notes here and there in this 5-minute interim, but try to work through this problem. If you get through this problem graphically and get the answer, and there's still time left, then maybe either try one of those algebraic methods, see if you can work that out, or if you want to work ahead, you can look ahead to this one at the bottom here. So we'll come back in about 5 minutes and work through this one. Okay, so this one is very similar to the last one. So I did the same setup as before here. I think this is pretty straightforward, this bit on the left. Again, the important thing to realize is that the time of 3 hours goes with the faster speed, v plus w. That's the shorter time goes with the faster speed, and vice versa. So if we got those backwards, if we got, 72 equals 6 times b plus w and 72 equals 3 times b minus w, we would get the wrong answer. So we have to make sure that the correct rate goes with the correct time. I divided by 3 and 6 again, switch things around a little bit, and got some ordered pairs over here. So let's again go through and graph these. I see that W, I guess, goes from 0 to 12. And B, it looks like, goes up to about 24. So what could I do? Maybe something like increments of 6. Something like that might get me a pretty reasonable set of points. So for my first equation, I go through 0, 24. And again, these were points that I picked. You could certainly have picked different points. 6, 18. Looks like it's about there. And 12, 12. And those 3 points do seem to be on the line. So the 2 points determine the line, and the third one kind of confirms that that everything seems to be in order. For my second equation, b minus w equals 12, that goes through 0, 12. Goes through 2, 14. And for 16, these points are a little hard to plot on this plot, but I think we can estimate a solution here. Maybe that point 6, 18. We definitely see w equals 6, b equals 18 as the solution to equation 1 is 18 minus 6 equal to 12. Yes, it is. So w equals 6, b equals 18, of course in miles per hour, is a solution to this system of equations, and we can see that it's a unique solution. This is the only point that's going to be on these two lines. And similar to last time, we could use the calculator if we wanted to. We would have to solve these equations for one of the variables in terms of the other. So something like b equals 24 minus w, and b equals 12 plus w. So b would be what we're considering our y in the y equals screen here, and w our x. So 24 minus x and 12 plus x. As my two equations in my calculator. And I see from my picture, maybe I want to go from 0 to 12 on the x-axis. That looks good, but maybe 0 to 24 on the y-axis. Again, we're looking for speeds here, so these should be both positive. We should be in the first quadrant, and that's where we see our solution. Second trace, we're looking for an intersection, so we choose option 5. And because it looks like the point is right on the point of intersection, I'm going to go navigate off to the right a little bit just so I can see that I do pick one curve, I hit enter, I pick a different curve, I hit enter, and then some guess. And it does indeed find the point of intersection, 6 on the horizontal axis, 18 on the vertical. So the speed of the water is 6 miles per hour, speed of the boat is 18. Any questions on this? Oh, wrong way. There we go. Okay, so let's work through a couple more. Tickets for the community fair cost $12 for adults and $5 for children. On the first day of the fair, 313 tickets were sold for a total of $21.81. How many adult tickets and how many child tickets were sold? So what are we looking for? And give me a second here. OneNote is starting to misbehave, as it seems to do on occasion. Usually just restarting it fixes everything. Wasn't able to choose the different pen colors, and that's one of the first things that OneNote does when it's starting to glitch out. All right, so we have our tickets. We want to know how many adult tickets. Let's just give these the variable A. And how many child tickets? Let's give these the variable C. Were sold. I have two pieces of information. One is the total number of tickets that were sold is 313. And the second piece of information has to do with value. I know what the individual tickets cost, and I know the total revenue for the day. So 313 total tickets were sold combined between adult tickets and child tickets. So I know that adult plus child equals 313. And I know the total revenue for the day was $21.81. So I know we had $12 times the number of adult tickets. That's the total revenue from the adult tickets. Plus $5 times the number of child tickets. That's the total revenue from the child tickets. That combined revenue is my grand total revenue of $21.81. And this is my system of equations, my two equations into unknowns. Now, for this one, let's just jump right to the calculator. I'm going to try to solve these in some slightly different ways from going from one to the other. So instead of going through and graphing by hand, if I wanted to jump straight to the calculator, what would I do? I would need to solve both of these equations for one of the variables. Let's choose to solve for A. So we get A equals some stuff for each of the two equations. In the first equation, I just have to subtract C from both sides. In the second equation, it's a little more complex. So let me come off to the side here and solve for A. Well, first I want to isolate my variable term. I do that by subtracting 5C from both sides. And then I want to isolate my variable. I do that by dividing by 12 on both sides. And in terms of my calculator, A will be what I call Y, and C will be what I call X. I just go to my Y equals menu. Clear out my previous equations. And then I have Y equals 313 minus X. And here I got to be a little careful. If I just did something like 2181 minus 5x over 12, this wouldn't quite be right. Because remember, the calculator respects order of operations. I think I need 8 times here. I forget if the calculator's smart enough to not put a times there, but it's always good to be a little more explicit than usual when you're dealing with calculators or computers or anything like that, just so the behavior is pretty clear. But remember that the calculator respects order of operations. It does multiplication division first, so it will do 5x over 12, get that result, and subtract from 2181. But that's not what I want. I want 2181 minus 5x all over 12. So I've got to do one of two things. One thing I could do is split up the fraction myself. And I could just go back and make this 2181 over 12 minus 5 times x over 12. I guess I could do that. The other thing I could do to be clear is I could insert parentheses. This second delete just gives me insert, so I can insert something and not overwrite what is in there. So now I have in parentheses 2181 minus 5x, and that whole thing is divided by 12. That's exactly what I want. Either way, if you wanted to split up the fraction yourself with 2 divided by 12s, or if you wanted to use parentheses, either way is fine, but you've got to do one of those 2 ways. Okay, so now what window do I want? Well, I haven't actually gotten any ordered pairs, but I kind of know that, okay, I'm looking for A and C, and A plus C is like a few hundred. So it's probably going to be like a couple hundred or so of each ticket type, right? So maybe I'll try like 0 to 300 on both axes. I know that a reasonability condition is I have to have sold positive tickets for both. If I get a solution with negative tickets, I'm suspicious that either maybe I did something incorrectly, or maybe it's just a poorly constructed problem. That's always a possibility. But here I think I should have positive tickets for both. And so I should have, yeah, positive for both and a total of somewhere in a few hundreds. So 0 to 300 on both axes should get me an intersection in the first quadrant that I'm looking for. Okay, and there's my intersection. Going to be super hard to estimate this by eye. So here I'm going to lean on the calculator. Second trace brings up the calculate menu. 5 for intersect. That's my first curve, that looks good. Second curve, that also looks good. And guess, just hit enter again. Doesn't matter where our guess is. And I see I get the solution that x, or in other words, C, equals 225. And y, or in other words, A, equals 88. So we sold 225 child tickets and 88 adult tickets. So that's our solution that, and we could check that, we could plug back in and see that 225 plus 88 is indeed 313. That looks good. And then we could use our calculator and check that 12 times 88 plus 5 times 225 equals 2181. And I have no doubt that that's true. But we, could check that if we were on an exam or something and the stakes were higher. Now, if we come over here, as an aside, I'm just going to do this one algebraically as well, just to show another example. So in this case, maybe I'll choose to use the addition elimination method. Now, up above, when I used that method, my equations were set up super nicely so that just by adding the 2 equations together, I immediately got a cancellation. Down here, we're not quite so lucky, right? If I just add these together, I get 13a plus 6c equals some big number. That doesn't really help me out. I just get one equation and two unknowns. That's not super helpful. I need to do one more thing here. I need to be a little creative and figure out, can I transform one of these equations into a form that sets me up so that when I add the two, one of my variables goes away? In this case, I'm going to take equation 1 and multiply by -5. I could multiply by -12 as well, but here I'm going to multiply by -5. Why am I doing that? Well, let's see. What happens when I do that? I get -5a minus 5c equals -5 times 313 is negative what? 1565. Hopefully I did that right. 5 times 300 is 1500, and 5 times 13 I think is 65. That looks good. And then I'll just copy down the other one. And I see that by transforming this first equation, I now have a plus 5c and a minus 5c. When I add these two together, when I just add straight down the columns, that plus 5c and minus 5c go away. So I get 12a plus a -5a is 7a. My c's go away. Minus 5c plus 5c, they go away. Equals 2181 minus 1565. Now I'll come over to my calculator, do 2181 minus 1565. That's 616. And I get that a is 616. Oops. Wrong screen. There we go. And then I can just hit divided by 7, and the calculator will reference the previous answer. So 616 over 7 is 88. Adult tickets sold. And then I could come back up and use one of these original equations with a equals 88 to solve for c. So for instance, I think the easiest one to use will be 88 plus c equals 313. C is 313 minus 88. Or 225. Just can't get my boxes right today. So the algebraic method, in this case, we had some bigger numbers, so it was a little harder to solve. We had to use the calculator to do some of the arithmetic. Over here, with the bigger numbers, it was easier to use the calculator to do the graphing. So when the numbers get bigger, it's, you're using the calculator a little bit more. We probably could have done both of these by hand if we had really wanted to, but the arithmetic would have ended up taking longer than the algebra. Okay, let's pop over here and look at this next example. Julia and her husband own a coffee shop. They experimented with mixing a city roast Colombian coffee that costs $7.80 per pound with a French roast Colombian coffee that costs $8.10 per pound to make a 20-pound blend. Their blend should cost them $7.92 per pound. So they want 20 pounds at $7.92 per pound of cost. And how many pounds of each type of coffee should they buy to make their total of 20 pounds at a cost of $7.92 per pound. So again, take about 5 minutes or so, work through this. And as usual, I'll jot some notes as you're working through, and we'll come back in 5 minutes and discuss. And I put the next one on the screen as well, in case you want to work ahead. Okay, our 5 minutes is up, so let's take a look at this problem. So let's call the oh, I circled the wrong thing. Let's call the city roast coffee C, and let's call the French roast coffee F. So C will be the number of pounds of city roast coffee that we're mixing, and F the number of pounds of French roast coffee that we're mixing. I note that I need to make a 20-pound blend. So that's my first criterion, that the amount of city roast plus the amount of French roast has to total 20 pounds. And that gives me my first equation. C plus F equals 20. Not bad there. The next one's a little bit tricky. So we want a certain cost per pound of the blend. So I might initially think something like 7.8 C plus 8.1 F equals 7.92. If I'm, not being super careful, I might think, oh, that's just kind of the mixture between the two. That I have $7.80 per pound times C pounds, or $7.8 per pound times C pounds, and then $8.1 per pound times F pounds for the French roast Colombian coffee. Now on my left side, I note that my units are dollars. The dollars per pound times pounds, the pounds cancel and leave me with just units of dollars. So on the left is something like the total cost, right? In this case, it would be the total cost for 20 pounds of this blend. On the right, if I'm being careless and I just throw in 7.92 and move on, I've actually made a mistake, right? Because my units I can see would not be right. If I just put 7.92, my units on the left are dollars, but my units on the right are dollars per pound. Very important that I multiply by 20 pounds. Right? I could see that if I think about it, the correct way to do it is to multiply by 20 pounds, because the left side is the total cost for 20 pounds of the mixture, phrased one way, phrased in terms of its component costs. And the right side is the total cost for 20 pounds of the mixture, phrased as the overall mixture cost. But again, if I didn't catch that at first and I was careful with the units, tracking them along the way, if I forgot about that last 20 at the end here, I would realize my units didn't match up and that I might want to look a little further. I would definitely like to use the calculator for this. I mean, 7.8, 7.92, 8.1, those don't seem like they're going to be super nice numbers to work with trying to graph this by hand. So I'll solve in terms of C. I mean, if you solved for F, that's not a problem either. I just chose to solve for C. So C is going to act as kind of my Y in the calculator, and F is my X. It's good to just kind of write this down explicitly so you keep it straight. So when you bring the answer back over from the calculator, you don't mix up the variables. So on one hand, we have Y equals 20 minus X. And on the other hand, again, we have this, big complicated numerator. So I just want to put in a parentheses. 7.92 times 20 minus 8.1 times, and F is being replaced by X in the calculator. That's the entire numerator. That whole thing gets divided by 7.8. So let me just double check that. 20 minus X, that looks good. 7.92 times 20 minus 8.1 times X, all in parentheses, divided by 7.8. That looks good as well. What should my window be? Well, again, the kind of a reasonability condition. I'm mixing two different types of coffee together. I want to make a total of 20 pounds. Well, the least I can mix together is 0 pounds of one or the other. It would be kind of an absurd solution to say that I need negative pounds of one of them and a bunch of pounds of the other. And the most that I could put in of either of them is 20 pounds. So I go from 0 to 20 on both axes. That seems pretty reasonable. And I actually, it was kind of hard to see, but my two lines have a very similar slope. So I think that my intersection occurred somewhere roughly in the middle of the screen, maybe a little bit to the top left. Maybe I'll change my window around a little bit. Maybe I'll go from, say, 5 to 10 on the horizontal axis. And maybe I'll try 5 to 10 on the vertical. We'll see if that gets us the intersection on the screen. Oh, I think I missed it. So I want to go maybe a little further over to the right. So maybe 5 to 12, something like that. And let's go a little further up as well, maybe 5 to 12. So we're getting closer, but even when we zoom in, it's actually still pretty hard to tell the two lines apart. If I go to second calculate menu, go to 5 for intersect. If I look on my top left, it'll indicate which line I'm on. So I'm going to use that here. Y1 is 20 minus X, that's good. And Y2, this big complicated thing, that's also good. My guess, whatever it turns out to be. And it does find an intersection at 8, 12. X equals 8, or in other words, F equals 8. And Y is 12, in other words, C is 12. I do see that 12 plus 8 is 20, so the first equation is satisfied. And if I check, I can check that 7.8 times C, or times 12, plus 8.1 times F, or times 8, that's 158.4, is that 7.92 times 20, fingers crossed, and it is. So our second equation is also satisfied. So that's our solution. It was really hard to tell based on the graph, even when we zoomed in, it's really hard to tell there's two lines. I mean, if you're not doing this on a graphing calculator in parallel with me, you might not even be able to see this on your screen. But you can barely tell there are two lines. They have a very similar slope and they cross right at 8, 12. Okay, so are there any questions on anything we talked about today? I think we're going to leave this last problem and a similar worksheet problem for next time because we only have 6 minutes left. I don't even think I'd be able to get through the lecture problem in 6 minutes, let alone be able to give you guys some time to practice and for us to discuss the worksheet problem. So we'll end a few minutes early today. And then give me about 5 minutes or so, 5 or 10 minutes. And then I will be in office hours. So I know there were a couple of people who had questions. So pop into office hours. I'll start the office hours meeting so you can get in, but give me until, a quarter after or so, and then I'll be in office hours.